All right, we seem to be asymptotically approaching about 25 participants here. So I think I will probably get started. So first of all, welcome. We're going to have this series of lectures this semester talking about the history of particle physics detectors. As we get towards the end of the semester, we'll be sort of moving into descriptions of like currently ongoing experiments. And I hope to have time at the end to talk a little bit about future facilities and how their requirements, specifications, desires, hopes, and dreams for future detectors are drawing on the sorts of things that we're doing right now. But for today, we're going to start sort of from the very beginning of the field of particle physics, going back at this point more than 100 years, about 125 or 130 years, to the foundations of the field. But before we do that, I just wanted to say a few words about me, where I'm coming from, and how the course is going to be organized. So there's going to be 14 weekly lectures. We start today, and we run for 3 months until what is close to the end of my semester here at FSU at the end of November. During that time, I'm going to assign 5 problem sets. So there's a subset of you who are taking the course for credit. And for those, your grade in the course will be based on those problem sets. But even if you're just auditing the course, I would encourage you to try the problem sets. And the main reason for that is that discussing the solutions to the problem set will be part of the lectures. So you'll get more out of that discussion if you've taken a look at the problem sets and at least attempted the problems before we discuss them. I will be holding office hours for the course to discuss the problem sets or anything else. I've changed the time of those office hours with respect to the original announcement. It's now 12 to 2 p.m. Central Time as opposed to 2 to 4 p.m. Central Time. I had a conflict. And I've updated the syllabus to reflect that as well. So these will also be by Zoom, but note that the Zoom link is different than the one for the lectures, just due to how I have my Zoom set up. So I hope to see you there. We won't really have time because of the size of the course to talk one-on-one with the students a lot during the lectures. So if you have questions about anything related to the course, or you just want to chat with me about pretty much anything, I will be happy to see you at those office hours. So what are my qualifications to teach you about this subject? I'm a professor here at Florida State University. I've been a member of the CMS experiment since 2005. Relative to some of our older colleagues, I don't have any experience actually on any experiment other than CMS, at least not large scale sort of full experiments besides CMS. I've done some R&D work outside of CMS. I got my PhD from the University of Notre Dame in 2011, where I did a PhD thesis measuring the photon cross-section, photon production from QCD, using conversions as a way to distinguish photons from the reducible background, mostly pi zeros. And during that time, I was also active in the installation and commissioning of the legacy CMS eCal, where I concentrated on electronics and operations. I then did a postdoc at Maryland from 2011 to 2016, where I did searches for top partners in the context of SUSY. I worked on the phase 1 upgrade of the CMS HCal, as well as HCal operations. And then towards the end of that time, I transitioned into being the Exotica long-lived particles co-convener, and I did analysis also in that group. I've been at FSU now for 8 years, since 2016, where my specialties have been analyses using long-lived particles. I'm one of the main people driving forward the HGCal upgrade project, in particular the scintillator SIPA-Montiel part, as well as the associated readout electronics for that part. And I'm also doing some Higgs physics here. So maybe I'll make use of the feature of Zoom that allows me to do a poll, if I can get that up, just to get some idea about you guys and your background. So let me start that. So I'm going to ask you guys to fill in this poll, whether you're an undergraduate, sort of a beginning graduate student, an advanced graduate student, or already have your PhD. So. All right, so hopefully you can see that poll now. One more second to answer. All right. So I'm going to share the results. So we have a few undergrads. We have a significant number of people who are in their first couple of years of graduate school. It seems like the most common answer was more than 2 years of graduate school, and we have a few people with their PhD, which includes me. So I think that, hopefully the level at which I've pitched the material will be appropriate to you, sort of regardless of which of these bins you fall into. Some of you may have heard a lot of these stories before. For some of you, it may be new. I'm always interested in getting feedback from you guys on how the course is going. So if something is really interesting to you and you want to hear more about it, please share that feedback with me and we can try to do that. And conversely, if I'm spending a lot of time on something which you already know or isn't really relevant, I appreciate that feedback too. I mean, I'm trying to produce, these lectures, not just for this audience, but sort of for posterity as well. So please do share with me any feedback you have about the level of the material or topics which you wish I had covered or wish I had not covered. Let me stop that. All right, so when I was sort of organizing the course, I was thinking about, what are the organizing principles? This is a very complex subject. It pulls in a lot of information, not just from sort of the history of modern physics and then moving towards the Standard Model in the second half of the 20th century, but, it also interacts with some topics in electronics, basic E&M, material science. There's a lot of stuff going on in high energy physics. So how can we organize a course so that it's not just like a laundry list of factoids? And what I'm really interested in doing with this series of lectures is trying to tell a story that explains why high energy physics ended up having the look that it currently does. So, in the early years of high energy physics, a photograph like this one would have been sufficient to claim discovery of a new particle. So this is a chamber where the experimenter may directly observe the interactions of single particles with his experiment. Usually it was his experiment at that time. There were some her experiments too. Observe the interaction of single particles with the apparatus on a tabletop. And, how did we get to something like CMS, a facility where a billion super complex interactions, each of them having hundreds of particles involved, if not more, are taking place each second, right? So there's a reason to scale up the complexity in this way. Can we follow sort of intellectually how the field developed such that a super complicated experiment like CMS is the logical next step in pursuing the science? Another way of thinking about it is in terms of people. So here is a picture, again, from the early part of the 20th century. This is Henrietta Blau sitting by herself at a desk. I mean, it's a posed photograph, but a lot of her research was done this way, basically looking through this microscope at interactions captured in nuclear emulsions in her case. And then she is disseminating the results of her science mainly by writing letters to people. So part of that is a technological story about how we've improved our communication over the years. But not only have we improved communication, but we've also really radically changed the social organization. So here's a picture from one of our CMS summer parties several years back. So we've transitioned from the lone experimenter working in the lab to experiments which have many thousands of people working in parallel on hundreds of different analyses and research problems, and linked together by high bandwidth electronic communication, like the way that we're running this class. So that's an interesting story worth telling, I think. And finally, or second to last, I should say, the sorts of evidence that we use in order to claim discoveries have really changed. So here's a diagram, again, from the early part of the 20th century, which is a hand-drawn diagram, which is showing the interactions of individual particles as points on the graph. And this graph at the time was considered to be sufficient proof of new phenomena. Here, the experimenter is illustrating that there exists something like the electron, but with a much lower energy loss per unit length in the experiment than electrons. But it's sort of very lo-fi. And now we do analysis at very high level of abstraction. So here's a plot from a Higgs paper a few years ago, TTH observation paper, showing all these different channels that were combined in order to show evidence of this new process. And actually, each of these analyses, if you were to go and look at the documentation, is itself incredibly complex and usually also working at a very high level of abstraction from the individual events. We employ lots of techniques like machine learning to do our data analysis, and there's probably no individual person in CMS who could do an analysis all by themselves, right? We're all building on the work of software, detector experts that all have to be combined in order to really produce anything out of the experiment. So how did we end up in that situation? And the sort of unifying story of all of that is how we built up our image of what matter and forces actually are. So when we start this story, we have a mental picture of atoms that looks something like this. People know from chemistry that there's a positively charged component of the atom, and there are negatively charged components called electrons, which we can sort of more easily add and subtract from the atom. And we know that chemistry happens when we combine different elements. They can exchange electrons with each other in certain sort of predictable ways, and we can form new compounds and release energy. And that picture by now is much more complex. There's a famous cartoon of the Standard Model that you see in practically every particle physics talk. But there's an enormous amount of information compacted here. And it was the process of filling out this chart that led to and drove all of the changes in organization and technological sophistication on the previous slides. I like this slide because it emphasizes something about high energy physics that I've always found to be a little bit unique and interesting, and that is the extent to which high energy physics is sort of a trading zone between people of different expertise. People, physicists, but also electrical engineers, mechanical engineers, people who are experts in providing sort of the care and feeding of the services that we need to run our experiments, people who handle the money that make the experiments go, are all meeting together and kind of transacting business with one another. And it's through these transactions that the science emerges. I think this is true to some extent for almost any physical science, but even within physics, I think high energy physics is an outlier in terms of how much this is true. And another way of getting at that is this quote from the historian of science, Peter Gallison, who talks about sort of the breadth of things that a high energy physicist might be expected to know in order to do their job. So he says, The life of an experimenter involves knowing, for example, the properties, costs, and uses of materials. Bubble chamber experimenter in the 1980s knew not only about heavy quark decays, but also about the tough, transparent plastic lexane, who manufactures it, what are its optical qualities, its tensile shear and temperature resistant strength. In short, about the many properties that made lexane ideal for canopies on military jet fighters and justified its existence, but made it equally well suited for holding vats of bubble chamber liquid. An emulsion physicist in the 1950s might well have attended conferences about film, with industrial workers more interested in photography or colloidal chemistry than pions. And a colliding beam experimenter needed to learn not only about rare decays and Higgs searches, but also about computer and electronic problems associated with an environment of intense radiation. Indeed, the only other workers interested in such environments were electrical engineers as they prepared radiation hardening for war on a nuclear battlefield. The effects of high bursts of radiation on delicate circuits led into a technical world altogether unknown to the particle theorist. I feel like this quote does a good job of capturing all those different perspectives that the experimental physicist needs to bring to bear in order to do high energy physics. So in this class, as I said at the beginning, our goal is to take a historical perspective on the development of the field and the development of the detectors and understand a little bit more detail how we ended up in this situation where we're applying technologies from the Cold War nuclear battlefield or what have you to our experiments. And in order to start that story, there's many places that you could start the story, but I'm going to start with Rutherford's experiment in 1900. So what does Rutherford do? He's what we would call today a nuclear physicist, but at this time, there's not really any distinction between nuclear and particle physics because particle physics hasn't really been invented yet as a discipline. It was already known at this time that there are certain elements and certain isotopes of those elements in the modern way of thinking about things, which produce ionizing radiation. In 1900, people already knew that ionizing radiation came in the form of particles because we can see individual events. In this famous experiment, you have a beam of alpha particles coming from a radioactive sample. You put it in a box with a hole in it so that instead of flying every which way around the lab, they're coming out of this box in a collimated beam. And then into this beam, you place a gold foil. The reason why you use gold as opposed to some cheaper metal is that gold is very ductile. And so it's easy to roll gold into a very thin foil, which is only a few atoms wide. This property of gold we'll see used in a few other places as well. So you can roll out this foil very, very thin, such that most of the alpha particles will penetrate through the foil, having interacted only with the electrons in the material. Since electrons are so much lighter than an alpha particle, an interaction between an alpha particle and an electron doesn't result in a very large deflection. But once in a while, and the rate of this is sort of proportional to the fraction of the total cross-sectional area of the atom, which is taken up by the atomic nucleus. So at the sort of rate of that ratio, you will sometimes see alpha particles deflect off of a nucleus in the gold instead of an electron. And in that case, they can be deflected through a very large angle or even reflected back completely in the direction of the source, which is very surprising if you have this sort of model of the atom in mind, which people tended to believe in those days, which was that there's a sort of diffuse blob of positive charge with electrons embedded on the surface, the so-called plum pudding model. In further experiments of this type, by using different isotopes, different elements, Rutherford is able to determine that there's at least 3 types of ionizing radiation. He names them alpha, beta, and gamma. We still use those terms today. And they're sort of arranged in order of how able they are to penetrate the material, with gamma rays being the most penetrating and alpha particles the least penetrating. So this is sort of what I would say is the state of play at the beginning of particle physics as a discipline. You know, experiments of the type that Rutherford did will be further developed in the direction of nuclear physics bombarding one isotope with another to produce new nuclides, et cetera. We may talk a little bit about that in this course, but I want to sort of go in a different direction and start talking about how people discovered cosmic rays, because cosmic rays not only sort of are the first place where the techniques of particle physics in a sort of recognizable way are used, but cosmic rays, in fact, still to this day, form one of the best sources of particles to study, and that's because of the incredible range of energies which we can access with them. So some of you may have seen or may remember seeing, for example, in an introductory class in E&M, this device called the electroscope. For example, when I teach E&M, I use this to talk about the phenomenon of induced charge. So the electroscope consists of a vessel, which is usually filled with an inert gas, perhaps at a low pressure. The vessel's made of glass, which is a pretty good electrical insulator, although not completely perfect. Usually there is a metal foil attached to the inside of the glass, which then is connected to an electrode, which comes through the glass to the outside. And in most of these experiments, that electrode will be grounded. And then there is a plug in the top of the glass bottle, which is made of an insulating material like rubber. And through that plug, you put a conducting rod. In this picture, it's made of brass. And to the end of that rod, you attach a little piece of gold leaf. So maybe if someone wants to raise their hand, have they seen this instrument in operation, and can they explain what it does? Anybody have any idea? What's the purpose of the gold leaf? What's going to happen to this thing if I, for example, bring a charged object close to the brass disc at the top? Anybody have any idea? Go ahead, raise your hand. Yeah,
may
go
I
ahead.
talk about that?
Please do.
Maybe when you near some of the charged object near this electroscope, you can see that if these have the same charge and we have the different charge, this golden leaf we have near together and close it when they have opposite charge together. But if they have a different charge, they are far away from that.
So that's pretty good. I think you got the main point there. So what happens, for example, if I bring so I can charge up, for example, a plastic rod through static electricity, right? I can take a plastic rod and I can rub it with a piece of fur or a piece of cloth, and I'll strip electrons. I think it's strip electrons off the cloth that stick on the rod. Maybe it's the other way around, but I end up with this rod which has a net charge. If I bring that thing towards the brass disc, let's say that my rod is positively charged, that's going to attract electrons in the brass, which are free to move. It's a conductor. They're going to get sucked up towards my positively charged rod. And then that will leave a net positive charge on the part of the device, which is inside of the bottle, right? So this gold leaf in particular will have an excess of positive charges in the situation that I just described. Because the gold leaf is so light, this excess charge is able to push, if there's an excess of positive charges on the gold leaf, these little wings will kind of open up and fly apart from each other. So the electroscope is basically a way of measuring with a physical device how much excess charge there is on the part inside the bottle. Okay, and so what people noticed is that if I do this exercise, and I have the leaves open up because of an excess of charge, same like charges repel on the leaf, and I just sit in that situation, what I will see is that over time, the leaves will go back down. They'll start to fall back down towards zero. So at first, people figure this is a instrumentation problem. So people have various theories about why you can't hold a charge on the leaf. Some of them are true. I mean, for example, it's hard to get all the water vapor out of this thing. Water vapor is a conductor. Even at low pressures, eventually it will conduct electricity from the gold leaf to the grounded metal foil and get rid of your charge. So people spent a lot of time improving the sealing of the bottle, blowing it out with dry air of better and better purity, sealing up any cracks or gaps that might allow the vapor to get in. And no matter what anybody does, using special materials covering the bottle in a varnish, which is supposed to be a better insulator than the glass, et cetera, et cetera. This phenomenon where the charge eventually dissipates, it can't be made to go away. So people came up with a hypothesis that the reason that the charge will always eventually drain away from this electroscope is that there's radioactive materials around us, right? In the crust of the earth, but also in man-made objects in the lab, which are ultimately coming from the earth. And so the theory is that radiation from the crust of the earth is penetrating the bottle. It produces ions inside the electroscope. Positively charged ions move towards the negatively charged part and vice versa, and eventually discharge the scope. So that's a good hypothesis. Does anyone have any idea how we could test the hypothesis of whether it's natural radioactivity which is causing the electroscope to discharge? What might we do with the electroscope to try to take it away from sources of natural radioactivity? Anybody have an idea? Go ahead and raise your hand in Zoom if you know how. Marguerite,
Lead bricks.
can you say more about that?
Just, surround it with lead bricks as much as you can. Other things to put a lot of radioactive length. Sorry, that's the wrong word. Material.
Yeah, so you could shield it from the environment and try to cut down on it that way. Interestingly enough, if you try this in the real world, you might actually find that your electroscope is going to discharge faster when it's surrounded by lead bricks than if it's surrounded by nothing at all. And nowadays we know that that's because unless you go to some amount of trouble to source lead from which the radioactive isotopes of lead have been removed, the lead itself can be a source of ionizing radiation. Another idea that they had was to try to take this electroscope to places where there shouldn't be any radiation from the Earth. In particular, you can try to take it to high altitude. So this guy, Wolf, he was a Jesuit priest and a physicist. That's why he's wearing the collar here. He invented something called the Wolf electroscope, whose principle of operation is identical basically to the one with gold foil, but instead it uses these metallized quartz fibers. That's what this German means, metallized quartz fibers. And they're sort of attached at the top and at the bottom. So what you're looking for is the sort of degree of separation between these things. As the electroscope discharges, this distance shrinks. And then you have a microscope looking at that little configuration with some markings on it that allows you to measure quantitatively how much it shrinks. And by comparing that with your watch, you can calculate a rate at which it shrinks. So his original idea was to build this more rugged electroscope that you could, for example, carry up the stairs of the, in his case, the Eiffel Tower. So his idea was, if I'm up at the top of the Eiffel Tower, I'm further away from the Earth. I'm further away from the radioactive isotopes in the Earth's crust, and I should see a decrease in the rate at which my electroscope discharges. So in 1909, he did this experiment. He took his electroscope of his own design up the Eiffel Tower, and he did observe a lower rate of discharge than at ground level, but still higher than what he had expected. People at this time already knew that there was a certain range that ionizing radiation would travel through matter, even air. And so based on that range, he did a calculation of how much less discharge he should see at the top of the Eiffel Tower versus the bottom. And while he did measure a decrease, it was not compatible with the effect that he estimated. And we now know that this is due to the fact that there's also radioactive isotopes in the metal of the Eiffel Tower. But people were still figuring that out at the time. All right, so good idea. Some decrease is seen, but the theory doesn't really make sense in quantitative terms with what was observed. The person who eventually sort of cracked the case was named Victor Hess. So he had the idea to use a hot air balloon in order to reach much higher altitudes than one could by simply climbing a building. In 1912, he started taking the electroscope of Wolf's design into a hot air balloon, and he did several sets of flights, eventually reaching an altitude of about 5.5 kilometers, so 15,000 feet, 17,000 feet, something like that. And what he found was totally shocking to people at the time. As he started going up in the balloon, he found a steadily increasing rate of discharge as the balloons went higher and higher. So this is contradicting the theory that the discharge of the electroscope is due to ionizing radiation coming from the Earth, because the further away he gets from the Earth, the higher, not lower, rate he observes of discharge in the electroscope. Originally, his idea was that this must be ionizing radiation which comes from the sun. Naively, I would think that the solution to this would be to do a flight at night, but maybe that's too dangerous or something. Instead, he had access to a location where a solar eclipse was scheduled to take place. And so he did one of these balloon flights during the solar eclipse with the idea that if ionizing radiation comes from the sun, the moon should be an effective shield. And what he found is that, in fact, the rate of discharge does not change during a solar eclipse. Another person who was doing similar investigations at the time was this guy, Jacob Clay. He was a Dutchman working in a team with his wife, Tetja, who I could not find a picture of. I'm not sure if one exists. But they have the idea to use the Earth's magnetic field to determine if the cosmic rays, which is what people are starting to call them at this time, given the results of Hess's experiments, it seems that the cosmic rays are coming from outside of the Earth's atmosphere. And he was interested in the question of whether these are charged rays like alpha rays or beta rays, or if they're neutral like gamma rays. It was already known at this time that the angle between the Earth's magnetic field and the surface of the Earth is changing as a function of your latitude. And so what he did was take one of Wolf's electroscopes down to the Red Sea, and then continue making readings as his sailing ship went from the Red Sea through the Suez Canal and back to Europe. So over this journey, you go from about 15 degrees orientation of the field lines of the Earth to closer to 50 or 60 degrees by the time you get further north. And what he sees here is that the ionizing radiation never goes away completely, but that there is a definite dependence on the amount of radiation reaching the Earth's surface based on your latitude. And from this, he concludes that at least some component of the cosmic rays must be charged, and that the magnetic field lines of the Earth are steering these particles away from his electroscope as a function of his latitude. So from Hess's results, we can infer that the source of the ionizing radiation is outside the atmosphere. From this, Millikan coins the term cosmic rays. But the electroscope as an instrument is rather limited. It's only able to measure one thing, which is the rate at which it discharges, and it doesn't provide much information about the type. Rutherford by 1903 had already identified alpha, beta, and gamma rays. We know that some component of these cosmic rays is charged based on Clay's experiments, but we don't know, for example, if it's made up of these 3 types of radiation which Rutherford identified or something else. And so it would really be much better to have a detector that can determine the composition of the cosmic rays, perhaps, for example, by imaging the interactions more directly. And this is something that you will find recurring throughout the story of high energy physics. Often new particles or new phenomenon are going to be inferred indirectly from the results of an experiment. And then somebody else will go out and build an experiment to sort of reproduce this in the lab in a way which is more convincing. So to be able to get a photograph or a photographic emulsion or something, which you can literally point at and say, well, here's the particle coming in, and here's how it interacts with the matter. In order to explain how people started to be able to do that, we're going to rewind again back to the latter part of the 19th century, September 1894. This is a picture from the top of a mountain in Scotland called Ben Nevis. Very picturesque. You see these sort of snow-capped peaks, and there was an observatory on top of this mountain which people used to observe clouds. Clouds are something that the United Kingdom has in copious supply, and so an observatory on top of a mountain in Scotland is a great place to observe, for example, the interaction of sunlight with clouds, which is what this guy C.T.R. Wilson's main interest was as a physicist. So he was trying to make measurements, for example, of how much light penetrated through different types of clouds. I think what he was really interested in was trying to estimate like how much water vapor there was in a cloud, whether this differed between different types of clouds, which look visually different, et cetera, et cetera. So he goes up this mountain of Ben Nevis, he takes some measurements, and then as many scientists have concluded over the years, he thinks, boy, it's really a pain to have to journey so far to do field work in order to get clouds. What if I could produce clouds in my own laboratory and make the measurements directly there without having to climb a mountain? And so he starts working on various apparatuses in order for him to be able to manufacture clouds in his own lab. He decides to build what he calls a cloud chamber, such that he can create a cloud in his own laboratory and then do better calibrated experiments about the scattering of light. It had been known already since about 1880, so 15 years prior, 16 years prior, that dust played a role in the nucleation of the water droplets that make up clouds. And so he already knew that he would have to control the level of dust in his cloud chamber in order to be able to produce the desired results. And so he started making experiments, if I filter and clean the air, can I affect the rate of cloud formation? What he found was that so there's a couple different free parameters that you can have for this experiment. One of them I just mentioned, which is to filter and clean the air and try to get more dust out of the air. This, all else being equal, should reduce the cloud droplet formation. The other thing that he can do is change the amount by which he expands the chamber. So the way that this apparatus works is that you have some water vapor in here along with some regular air. You basically have this bellows, this brown part at the left. So you pump in moisture-laden air under pressure, and then you allow this bellows to open. It expands the volume and rapidly cools this vapor-laden air, and under the right conditions, that will cause droplets to form. So what Wilson was investigating is sort of what is the trade-off between the amount of the expansion and the amount of dust in the air. So he kept reducing the dust concentration in his cloud chamber more and more, and seeing how large of an expansion in volume would be required to form clouds with this cleaner and cleaner air. And what he realized is that even if he cleaned the air as much as he knew how, used the best filters available, et cetera, even under those conditions, if he did a large enough expansion, he would still see droplets forming. And basically, you can run this experiment over and over again. Each time that you do the expansion, any remaining dust that's inside, the droplets will nucleate to it, and it falls basically to the bottom of the chamber. So you clean the air successively by doing multiple rounds of expansion. And he found that no matter how many rounds he did, there was always some residual chance for clouds to form. So this was a puzzle. He had some idea that droplet formation might be related to ionizing radiation. His idea, which was a very smart idea, was that, we know from other experiments in chemistry, whatever, that water is a polar molecule, meaning that it has a residual electric charge across the molecule. And so his idea was, well, maybe I can study the effect to which ionizing radiation, in his case, he was using X-rays, could influence cloud formation. So he got some really good quality cameras. He brought an X-ray source near to his cloud chamber, and he started taking photographs like this one. So can somebody explain to me what we see in this picture? So this is, he brings the X-ray source close to his cloud chamber. He does the expansion. This rapidly cools the water vapor so that the liquid water wants to come out of the solution, droplets form. And what do we see here? What are these little trails? Can somebody explain this picture to me? Go ahead, don't be shy. What are these tracks? Anybody?
Oh,
Go ahead,
may I explain?
please do.
Maybe it's the heat of the particles by the energy or momentum or some of the properties of that.
So you think what we're seeing is heat energy, which is deposited by radiation, and then what? Why would that cause droplets to form? So the key word here is ionizing radiation, right? X-rays are a form of ionizing radiation, which means that when I expose a material, in this case, water vapor, to X-rays, X-rays have sufficient energy to actually knock an electron out of the atom. This can even be an electron from deep inside the atom because X-rays are much more energetic than just the valence electrons in the material. So what happens here in this picture is that an X-ray hits a water molecule and pops out an electron, and then that electron is going through the water vapor, colliding with other water molecules. And for a while, it has enough energy. We're talking about many keV of energy, whereas the typical binding energy of an electron in a water molecule might be some number of EV. So when a high energy electron gets knocked out by an X-ray, it's going to careen through the material like a ping pong ball, knocking electrons off of individual water molecules inside the chamber. And each time it does this, what's left over is an ion, an ionized water molecule. Because water is polar, that ion, having probably most of the time a positive charge, is going to attract the negative ends of nearby water molecules towards it. And that's what initiates the droplet formation. So each little dot that you see along these tracks is an individual water molecule, which was ionized by either a primary X-ray hitting it, but most of them are not that primary X-ray, but actually the electrons, which are knocked off by the primary interaction. And then that high energy electron is knocking through the water, creating a trail of ions along the way. Each of those ions then acts as a nucleation site for the droplet. So what we see here are actually the paths of individual electrons visible in a photograph. And so even though he started out studying the interaction of light with clouds, Wilson ended up keying onto something which at least I think is far more interesting, which is that you can actually use this technology to produce images of the path of individual charge particles with a cloud chamber. And this was essentially the dominant technology in particle physics for the next 30, 40 years, basically from this discovery around the turn of the century until sort of World War II times. This was one of the main technologies driving discovery in particle physics. Ryan, did you have a question?
Yeah. Yeah, the question is, you were talking, Ted, about the water molecule like facing one way, and that's what's kind of leading to the droplets. Can you explain that a little bit more? Like how that actually leads to the droplets and the visualization of these tracks?
Yeah, so at each point along the so what we see here is the path of the electron, basically, as long as it is energetic enough to ionize other water molecules, right? So what ends up happening is you knock out an electron, an X-ray comes into the chamber and knocks out an electron from one water molecule and gives it a lot of energy, like keV of energy. So it has that kinetic energy to be able to ionize many other water molecules before it comes to a stop. Each
Okay.
time it ionizes another water molecule, that becomes a nucleation site for a droplet. And the reason is because water is a polar substance. So when I create an ion, the other water molecules in the vicinity are going to feel an attractive pull towards that ion because the sort of hydrogen side of the water molecule is positively charged. And so it will be pulled towards that ion, or vice versa. Actually, we're talking about producing positively charged ions. So it's the negatively charged side of the other water molecules which is attracted to it. Does that make sense?
Yeah, and then you were saying basically it's actually the kinetic energy that's transferred that allows the droplets to form, right?
The transfer of kinetic energy is what ionizes the water. And then once I have an ionized water molecule in the vapor, it will just attract other water molecules to it because water molecules have a dipole moment. Yeah. So if I just put a positive charged ion in the water vapor, other water molecules, even ones that aren't ionized, will still feel an attraction towards it because the water molecules themselves have a positively charged side.
Okay. I see. I understand. Thanks. Yeah.
Any other questions? That was a good question, Ryan. Thank you. So there turn out to be lots of phenomena which you can study using this cloud chamber apparatus. So one thing that people started noticing as soon as this would happen is that even without bringing any X-ray source, for example, near the chamber, you would periodically see events like this one. So here we have sort of a three-pronged track here, and this is the result of a beta decay of a radioactive isotope in the gas. So at one of these locations, I'm not sure it's really possible to tell which, but probably this one. Can you guys see my cursor? One of the interesting things about cloud chambers, and we'll see this repeated when we look at other kinds of charged particle detectors, is that we can actually derive some information about the energy of the particles, not just their path, from looking at how dense the droplets are along the track, right? The more energetic the particle is, the longer it will travel between successive interactions on average. And eventually, towards the end of its track, you'll see very many interactions in a small area. So you can kind of see the electrons, which are produced ionizing more and more as they slow down, and eventually they kind of fall into this big cloud of droplets at the end, and that's where the electron is basically ranging out in the material. And if you look carefully at this track, I think you can see the rate of ionization changing as it travels along. So you start out with this thing which is ionizing relatively infrequently. The mean free path is longer while the energy is high. Then I have here a event where I give up a lot of energy to a single electron, and I actually produce a second electron, which goes on its own little journey here. And then probably the initial electron here, which is deflected at that interaction, is slowing down, and the interaction cross-section is increasing and increasing until finally it deposits all of its energy towards the end of the track. So you can start to get an intuitive feeling for the interaction of electrons with matter just from the thickness or the density of these tracks. You can see the rate of ionization changing as the electron loses energy. And you can get that just visually from looking at the density of this track, getting more white as it goes. I can also put my cloud chamber into a magnetic field. So just as, sorry, there's a question from Bhavya.
Yeah, I just want to understand so when the track ends, what does that signifies?
I'm sorry?
So like what is happening at the end of the track? So the area of cross section is very high there. That means there's a lot more interactions there. But
Exactly.
why is it
So
ending there?
as the electron loses energy, it gets closer and closer to the typical energy of the electrons, which are just sitting around in the material bound to their atoms. And the interaction cross-section goes up as we lose energy. I'll have the slides with like the beta-Bach equation and a few slides explaining in more quantitative terms why this is. And then also as it, the higher energy it is, the less it's deflected by each individual interaction. So you see that when the track starts out on the left-hand side here, it's rather straight. It keeps going fast. And then as it starts to lose more and more energy, it gets deflected more and more by each interaction in like angular terms. And so it just sort of ends up at the end on this like random walk around this little area, depositing all the rest of its energy in a very small volume of space.
So it does not necessarily have anything to do with like a variable concentration of water molecules around those places, those spots.
Yeah, I think in all these pictures, you can assume that before any ionizing radiation is introduced, this is just a gas under pressure. It's like free to move around inside the vessel.
Right.
So the concentration of water molecules should be pretty much constant everywhere in the photo.
Okay. Thanks.
So one can also put your cloud chamber into a magnetic field, just as Clay had the idea to use the Earth's magnetic field to determine what the charged component of the cosmic rays was. You can do this to study, for example, only the interactions of gamma rays with the material. You put your cloud chamber in a magnetic field and add a gamma source, and the magnetic field will basically sweep away any charged particles which are trying to enter. You can actually see here in this picture these little circles which are produced around the main interaction of interest. So these are probably lower energy electrons which are ionized from the material, and they basically just travel in these little circles because they're subject to the magnetic field. But what I want you to see here is actually this interaction here. So we see basically the initiating particle must be coming from the bottom of the picture, but it doesn't leave any track. And then suddenly we have two relatively high energy electrons, except one of them must have a different charge than the first because it's deflected in the opposite direction. So can somebody tell me what particle interaction have I imaged here? What happened here? There was a clue earlier in the talk when I described my PhD thesis, what this is. John.
Yeah, is this electron-positron pair creation?
Exactly. So we have a high energy gamma ray coming in from the bottom. it cannot convert into electron-positron pair in vacuum because the energy and momentum conservation doesn't work. But if it's in the electric field of an atom, then it can trade off enough momentum with the atom to be able to make this process happen. So the gamma ray comes in, and then it trades some momentum with one of the water molecules in the chamber, and we produce a high energy electron and what would later be identified as a high energy positron. So using this interaction, we can infer what the momentum of the originating gamma ray must have been. So this leads us to the discussion of how charged particles interact with matter. So we're going to kind of go back to the PDG for a few slides and remind ourselves about how this process works. So we typically describe the energy loss of particles traveling through matter in terms of the mean energy loss per path length, dE dx, where E is the energy and X is the distance. Be careful. There are many types of interactions between particles and matter, and the energy loss per unit distance can depend on many factors, which include the particle type, particle energy, as well as the electronic and nuclear structure of the material. So there's a wide variety of different types of interactions which can happen, but there are some sort of general things that we can say about how this process works. This is a picture of the stopping power, which is just the dE dx with a negative sign. So stopping power is like how much energy the material absorbs from the particle, I guess you could say it that way. So this is the mass stopping power for positive muons in copper as a function of their momentum. And you can see that there are a couple of interesting features in this plot. So for very high energy charged particles, the spectrum of energy loss is dominated by what we call radiative processes. So this is where so this is a positive muon, which is traveling through copper. So for very high energy muons, it's hard for the muon to really interact directly with the electrons or the nucleus of the material, just because its energy is so much above the characteristic energy scales of the electrons and the nucleus that it's very difficult kinematically to find an interaction to happen. But what can happen is that the electron will get, or sorry, the muon will get steered in the high electric fields near a nucleus. And any time that a charged particle accelerates, we know that it's going to emit radiation. So in the radiative part of this plot, what we're mostly seeing is that the muon is zipping through the material at very close to the speed of light. It makes a close approach to a nucleus, and it feels the strong electric field of that nucleus, and it gets accelerated a little bit, changes its path a little bit, and it will emit a photon, which can be quite energetic. Those of you who do analysis on CMS, you may know that like one of the things that can happen with very high momentum muons in an experiment like ours is that you will have these high energy Bremsstrahlung events from very energetic muons that will cause then that emits a high energy photon, which itself will undergo then an electromagnetic shower. For those of you that don't know what I'm talking about, we'll talk more about the showering process in the future lecture. Then as the momentum goes down to sort of the tens or hundreds of GeV range, the radiative effects start to peter out, and we enter this regime called a minimum ionizing particle. And this is a convenient benchmark for us as physicists because a lot of the muons in our experiment, for example, muons that are coming from the decays of vector bosons, whatever, things that we're interested in doing high energy physics experiments on, a lot of them just tend to fall into this realm of, let's say, 100 MeV to 100 GeV, where we're not exactly at the minimum ionization, but close enough that it's a good approximation for analyzing the behavior of the material. But so physicists will throw around this term MIP a lot to refer to minimum ionizing particles, but it's important to recognize that technically there's only one specific energy for a given type of particle and a given material, There's only one specific energy that's really the minimum ionization, but it's a good approximation. You know, this is a log plot. So it's a good approximation for the behavior across a wide range of energies. That's kind of the most relevant to us in our experiments a lot of the time. But of course, if I'm looking at ultra high energy cosmic rays or something like that, I'm going to be mostly interested in this part of the plot. And then there's other processes that turn on at lower energies. And that's where the muon starts to have a closer sort of energy to the electrons in the material, and it opens up a lot of interaction cross-section with those electrons, and you have this other peak down here. So if I change the particle type or I change the material type, it will sort of shift the points on this plot around to some extent, but it's a general truth that at very high energies for any charged particle, the radiative losses are going to dominate. Then we go to a regime of minimum ionization where the interaction between the particle and the material is minimum or close to minimum. And then as I further decrease the energy, I see a large increase in the stopping power, a large increase in the probability of interaction. So we often are talking about this particular part of the plot, but it's important to recognize that depending on the specific experiment that you're doing, you might also want to be concerned with the other ones. So there's something called the beta block equation, which is basically tailored to the situation where I have a heavy particle. Here, heavy means the mass of my particle is much larger than the mass of the electron. So this is true for muons, it's true for protons, but it's not true for electrons, which have a different kind of typical interaction. And so in this domain where we're dominated by collisional losses with the electrons, we get this beta block formula. And I'm just going to try to motivate for you what the different parts of this equation are for. So we have the normal thing dE dx that we're trying to calculate. Sometimes you'll see people doing things in terms of instead of the path length, this is the path length in grams per square centimeter. So it's essentially subsuming the density of the material into the calculation, right? So normally when we're talking about absorbers in high energy physics, it's something like a metal where the density just is what it is. But of course, you can also have like gaseous detectors, in which case you control the density, right? You control the pressure that things are at. So this parameterization in terms of grams per square centimeter is especially useful in the case where I actually have the density of the material as a handle that I can change to optimize my detector. Then I have this first term here on the right-hand side, which is the electron density of the material. So we have Avogadro's number and the number of protons in the nucleus. So all else being equal, the higher the number of protons, the higher the number of electrons will be in the material, because these materials are electrically neutral. And so it makes sense that the energy loss per unit length will be higher, all else being equal, if the Z of my element is higher. We then have this funny looking thing here, which is inversely proportional to the square of the velocity of the particle. And this is basically just what is the strength. This is a calculation from electromagnetism, the scale of the energy transfer per collision. So the faster the particle is moving, the lower typically the scale of this energy transfer. And that's what's responsible for the increase in the dE dx as the particle loses energy. As it loses energy, it loses velocity, and this term starts to grow. And then finally, we have this third term, which is related to what's called the ionization potential of the material. Basically, the more protons there are in the nucleus of the material, the more strongly bound the electrons tend to be. Perhaps you've seen this plot that shows like the radius of an atom decreasing within a given shell as you increase Z. That's for the same reason that this ionization potential is increasing with Z. Just the electrons are more tightly bound to the nucleus when the nucleus contains more positive charge. Particle physics, we're often talking about the gamma value. There's relativistic gamma for particles rather than their absolute velocity. Typically, the MIP range is going to be reached for values of gamma around 3 or 4. So if we're talking about a muon, which has, roughly 100 MeV of rest mass, then we would expect this this minimum ionization peak to be at a value around 300 MeV or so, and we can check that against our plot here. So 300 MeV of muon momentum would be right here. So the behavior of this plot matches what we would expect from this beta block equation. And then the other typical value, which is good to keep in mind, is that for a minimum ionizing particle, again, it depends on the material and the particle species, but typical values at the minimum ionization regime are 1 to 2 MeV per gram per square centimeter. So if you know the density of whatever you're trying to shield muons or get muons to interact with your experiment, if you know the density of the material that you're using, you can kind of do a back of the envelope calculation for how thick your shield would need to be for particles to be absorbed by it using this sort of typical value. Because the amount of ionization depends on the particle species, different masses of particles will have their minimum ionization peaks in a slightly different place, and they will also start to range out in perhaps very different places. That's the principle behind a lot of particle identification systems. So when we're looking at these nuclear emulsions or cloud chamber photographs, we could kind of read off the energy loss per unit length by looking at the thickness of the track. Modern electronic detectors do this too, by measuring more directly the amount of ionization. If you have a gaseous detector, you can measure how much charge is collected on the electrodes. And this will tell you how much energy the particle lost traveling through a known length of gas. You can then go and look up on a plot like this one, for which mass of particle at this given momentum would I observe that amount of ionization. So this is a plot from the Elise experiment, which has one of these particle ID systems. And you can clearly see that the different particles behave sufficiently differently in terms of their energy loss per unit length in the same gas that for some momenta of the particles, you can efficiently separate the particle types just by measuring the ionization. So in one direction, you can think about, how much shielding or how much material would I need to absorb a specific kind of particle, but you can also go backwards in the other direction and say, given this amount of material, is the amount of energy loss that I observed consistent with the hypothesis of, say, a proton or a kaon? And this is a way that you might identify particles in your experiment. Another effect of this beta block equation is what we call the Bragg peak. So as we saw in the cloud chamber photographs, and as we saw from the plot of the muon energy loss as a function of momentum, eventually as particles give up momentum to the material, they lose energy, they slow down, and that increases the interaction cross-section. And the way that this works out in practice is that a significant fraction of the initial energy will be released just in the last part of the track. Think of those white blobs that we saw at the end of the cloud chamber photographs. So if you have a specific energy of particle, if you have like a monochromatic beam of particles, monochromatic meaning they'll have the same energy, then they will tend to give up a lion's share of their energy in a relatively short distance before they stop propagating through the material completely. And this is extremely useful for using radiation on materials. The example that I have in mind is cancer treatment. So you have a tumor in your body. The hospital can measure like how many centimeters deep the tumor is in your body. Your body is mostly made of water. And so you can calculate what specific energy of particles do I need to shoot into the body such that they will lose energy in just the right way to deposit almost all of their energy in the tumor as opposed to the surrounding tissue. And this is the principle that's used, for example, in proton therapy of cancer. Here is an illustration of this phenomenon from a cloud chamber photograph. So what we have here is a radioactive sample of, I want to say this is an isotope of thorium, but I don't think I have it labeled on the plot. So it gives out alpha particles of a given momentum, right? These radioactive decays happen when the nucleus decays from some higher energy state to a lower energy state. And that means that if there's only one such decay of the material available, that all of the alphas coming out will have basically the same energy. And so if you put this thing in a cloud chamber and then do the expansion to make the tracks visible, you see that like all of these alpha particles basically range out at the identical distance, right? They all travel to the same distance and then stop. And in fact, you can even see if you look carefully towards the ends of these tracks, the deflections start to become larger because the energy of the particle is going down. So you can even see that the track starts out completely ramrod straight and then kind of wanders a little bit at the end. And there you're basically seeing that break peak in action. The particle is losing almost all of its energy in that last part, and it starts kind of getting knocked around a lot more by the material as it loses energy. Now, we said that this equation was good for particles heavier than electrons, but of course, electrons are a very important particle to be able to deal with. And so we want to have an equivalent of the beta formula for electrons. And that looks like this. So electrons are mostly losing energy by interacting with the strong electric fields of the nuclei in a material. And this is kind of a very arbitrary thing. You've got 4z times z plus 1. You've got the number 183 in here. You've got something raised to the third power. So this is not as well motivated from first principles as the beta block equation, but it's basically fit to data. So these parameters like 183 are fit to data. And what we normally do in high energy physics is subsume all of this stuff except the E into a single number called X naught, or the radiation length for the material. So here's what radiation or energy lost by electrons looks like. It's quite different than the plot from muons, has sort of less features overall. We have this sort of flat, slightly increasing with energy bremsstrahlung. So that's the case where you're losing energy again by being steered in the strong electric field of the nuclei. And that cross-section changes a little bit as you lose energy, but mostly what happens is that as you lose energy down to 10 or even 1 MeV, the cross-section for ionization, that is to knock another electron out of its host molecule, goes up a lot, such that by the time you get below, let's say, 10 MeV of electron energy, this ionization totally dominates. If you would then extend this down to like EV of energy, you would see this turn over basically as the electron lost all of its energy and it no longer has sufficient energy to ionize anybody else. And normally in high energy physics, therefore, we're not so worried about this ionization part. I mean, 10 MeV is a very low energy for a high energy physics experiment. So we mostly think about this area of bremsstrahlung where the thing is pretty flat. And that's why we can get away with using just a single number to parameterize the energy loss by electrons. It's because over a wide range of energies, the bremsstrahlung cross-section is more or less constant, certainly to better than a factor 2. And therefore, instead of having to do the full calculation, we can just calculate the dx as E over X. Typical thing would be lead, which has an X naught of 6.37 grams per cubic centimeter, meaning that in a real world experiment, you're talking about distances on the order of a centimeter. So going back to our picture from before, we can then sort of reanalyze this picture with what we now know, so that there's a area where the electron is traveling, with sufficient energy that it's losing energy, at least primarily through Bremsstrahlung. And then as it slows down, this ionization process kicks in and gets sort of ever stronger as the electron slows down and loses energy. And eventually it sort of craps out and leaves all of its energy in this big white blob. These are pictures of high energy alpha particles in a cloud chamber. And I want to call your attention to these little kind of hairy guys growing out of the side. Can anybody tell me what those little things are sticking out the side of these alpha particle tracks? What do we think those are? I'll give you a clue. You may have heard them referred to as delta rays. Anybody have an idea? So along the straight part of the track, we have this very heavy ionization from the alpha particle. Remember, an alpha particle has 2 protons and 2 neutrons, so it's quite massive, but it's also highly charged. So it is just plowing through this water vapor, not really being deflected at all. And it's producing a lot of ions along the track. That's why these tracks are so thick. You can't resolve the individual ionization events. And what these little sort of hairs growing out the side of, we call delta rays. So those are cases where in a specific interaction between the delta particle and a molecule of the gas, the alpha particle transferred enough energy to ionize that water molecule with enough energy left over that the electron itself then goes propagating through the material. So these delta rays are high energy electrons produced by the interaction of the alpha particle with their parent molecule, but they have enough energy to then go on their own little journey and ionize other molecules before coming to a stop. So you can see this guy, again, it has that kind of characteristic look where it starts out ionizing and then dumps most of its energy towards the end of the track, right? You can see those kind of little Bragg peaks at the ends of these delta rays, and that's because the electron starts out with enough energy to ionize other molecules, and then as it's losing energy, it interaction cross-section grows and grows. We had the picture earlier of the photon conversion. So just to put some kind of more physics background to that, photons are neutral, so they don't lose energy by Bremsstrahlung or by any of the other mechanisms that affect heavy charge particles or electrons. There's basically 3 regimes of energy where the dominant interaction is different. For electrons below about 100 keV, we have what's called the photoelectric effect. Probably you remember that from your modern physics class. There you would have talked about electrons being freed from their parent atom by probably ultraviolet radiation, but this process goes all the way up to about 100 keV of incident photon energy. So basically that just means we give that energy to an electron. Above about 100 keV, the dominant process is Compton scattering. So that's kind of the sweet spot for the photon and the electron to have like a high momentum transfer where we end up with a fast electron being produced in the material, which then will lose energy along its track and eventually range out. And finally, above 1 MeV, it becomes kinematically favorable for there to be a conversion into an E+ E- pair. And that's what we saw in this picture here, the gamma ray entering from the bottom and converting into an E+ E- pair. So all of this just to kind of give you a sense for what particle interactions with matter look like, both in a quantitative sense and also in the images produced by cloud chamber photographs. I'm going to say a few words in the remaining time to kind of set us up for the next lecture, and that is to sort of recap what the state of play is around the year 1930 or so. So we've had these series of experiments on cosmic rays, which gave us some idea of what cosmic rays are made of. There's some charged component, possibly also some neutral component, but we don't know much about the components, what their actual particle nature is. So in 1930, a particle physicist would have been willing, I think, to sign on to the following. They know matter consists of atoms. Atoms consist of electrons and nuclei. That's the insight from Rutherford's experiments. The electronic structure of the elements is described by quantum mechanics, which is quite well developed by this point. The nucleus consists of A protons and A minus Z electrons, which result in a net charge of Z. So some of the electrons are confined to the nucleus, other electrons are further away in a cloud around the nucleus. Electrons and protons both have half integer spin, what we would call fermions. There's something called the alpha particle, or what we might now call a deuteron, or the nuclei of the deuterium isotope, and alpha particles, which seem to have similar properties to the deuterons, have integer spin. We call those bosons. And in addition to charged particles, we know that there's electrically neutral radiation, at least two types, X-rays and gamma rays. And we've understood that this is electromagnetic radiation. Basically, these are high energy photons of their various energies. X-rays typically in the like tens of keV, and gamma rays typically MeV and upward. So now that we have some basic idea about how someone in 1930 would have thought of this state of the field of particle physics, we're going to continue along with this understanding. So this is a interesting picture which was taken around this time, around 1930, and there's some really interesting physics that you can extract from this picture. So can anybody tell me, first of all, something about the spectrum of the incident particles going into this picture? Just based on the tracks that we see, what can we say about the particles which are coming into my cloud chamber? What are some features that you notice? Go ahead, John.
Yeah, it looks like they have a pretty wide range of path lengths. So I would say that there's probably a pretty wide spread of energies, or some spread of energies.
Yeah, there's definitely a spread, and I might even be prepared to argue that there were sort of two, like a bimodal distribution, right? There seemed to be some fraction of particles which are ranging out around this radius, right? We see a lot of tracks ending sort of in this regime. And then there seems to be a presumably higher energy population here. They're not all ranging out identically, so there may be some spectrum beyond that, but loosely speaking, there's at least two sort of distributions laid on top of each other. Then I will also call your attention to this interesting interaction, which is kind of unlike what we've seen before. I'll just toggle back and forth between the original picture and the annotated picture with the colored arrows. So there seems to be something like pretty interesting happening here. So we have whatever our incident particles are, it's one of these more energetic species because it's part of the population that travels further before ranging out. And then it seems like there's some interaction here, which is a little bit strange. So we have this guy coming in. There's some kind of interaction which happens here at the meeting point of these three arrows. And then what's produced is a particle which doesn't have very much range. It seems to range out pretty quickly afterwards, and we can see the track getting deflected towards the end. And then we have this super large angle scattering thing coming out of here. So this is bombardment with alpha particles. This is a thorium source. This particular isotope of thorium has two different decay paths with two different energies of alpha particle, which explains the differences in path length that we see from alpha to alpha here. And they used an automatic camera here. So this was a technology that was developed in the 30s to try to get larger numbers of events to look for rarer and rarer processes, which is going to be a theme we'll return to throughout the semester. So this thing would automatically expand itself and take a picture without any human interaction. So by just letting it run for like hours and days, you could accumulate lots of statistics. So this fully automatic chamber took 23,000 pictures during this experiment. And in each of those pictures, you had lots of different alpha particles. I think you could try to count here, but there's surely several dozen. Over the 23,000 pictures that they took with this experiment, they had about 400,000 alpha particles. And in 8 cases, they saw events like this one with this large angle scatter backwards and then this short track pointing forwards. If we label these with our modern understanding of what the particles are, we have the alpha particle coming in with high energy. It then undergoes some nuclear interaction with an oxygen molecule in the water vapor. It creates this different isotope. So we started with the oxygen 16. The alpha particle, one of the protons is absorbed into the nucleus. Sorry, this must be, we have 2 neutrons and 2 protons coming in, 1 proton coming out. So we incremented the number of protons by 1. So it must not have been oxygen on the target, but rather what's one spot before oxygen. This thing is heavy, and so it ranges out quickly. And then we have this proton zooming out backwards. So there's a lot of physics contained here. You know, people did a lot of nuclear physics using these kinds of experiments. And what I want you to take from this is that this combination of an automatic bubble chamber, which is expanding and taking pictures of itself, allows us to move into the regime where we can study relatively rare processes. So this is 8 events out of 400,000. So we're talking about processes which happen, you know, 1 time out of 10 to the 4th or so. Of course, we know nowadays that we're sensitive to processes which are much rarer than that. And one of the driving features of the development of these experiments over time is going to be how we can speed up this readout and recording process such that we can produce millions and eventually billions and even more events to look for increasingly rare phenomena. Anyways, I'm going to stop here for today. We'll pick up in the next lecture talking about the discovery of the positron and of the neutron. Are there any quick questions before we stop? All right, thanks everybody. I will see you next time.
Thank you.
Thanks.